Simpson's rule follows an idea similar to that of the midpoint rule or the trapezoidal rule, or the trapezoidal rule. And that is approximating the complex area, the complex shape under our curve with simpler shapes. And so in this picture, we again see a partition of the interval AB into subintervals. But it should be kept in mind that Simpson's rule is only applicable when the number of subintervals is even. So it's 2 times some number k. It cannot be 7, it can only be 8 or 6, and so on. And so the reason for that is, for Simpson's rule, we need to group intervals in pairs. Specifically, what we do is we first consider the first pair of intervals. So these two here. Now, for these intervals, we have 3 points on the curve. The two intervals have a total of 3 endpoints. They share one endpoint. And what we do is, through these 3 endpoints, we draw a parabola. There is a unique parabola passing through 3 points in the plane. It can be degenerate, so it can actually be a straight line if the 3 points are collinear, but if they are not, it's going to be an actual parabola. So through these 3 points, we're going to draw a parabola. So it's a bit hard to see. There is a blue parabola, so the graph of our function y equals f of x is in black, but there is a blue parabola that we draw through the 3 points. So once we have done that, the area under the parabola is going to be the approximation to the area under the curve. Then we look at the second pair of subintervals, these here. And similarly for them, we look at the 3 endpoints that they share, and there is another unique parabola, again shown in blue here, that passes through these 3 points. We compute area bounded by this parabola and so on. Then we just sum up all the areas of little parabolas that approximate the graph of our function. Now, the derivation of this rule is a little bit more involved, so we will skip it. I'll just give you the formula for the Simpson's sum. So the nth Simpson's sum, where n, again I want to emphasize, n is an even integer, is given by this formula here. So it's the delta x over 3, which is the length of a single subinterval in your partition, multiplied by f of x0 plus 4f of x1 plus 2f of x2 and so on. So here are the values of f at xi's. So again, xi's are given by a plus I times delta x. So the formula remains the same. But the coefficients next to these the coefficients are a little bit more involved than they were for even trapezoidal rule. So remember, for trapezoidal rule, what we would do here was putting coefficients 1, 2, 2, 2, and then the very last value of f also came with a coefficient of 1. Now, in here, for Simpson's rule, the coefficients look like so. So they start with 1, and then they go 4, 2, 4, 2, 4, 1. There's always an odd number of terms in total. We have an even n, and the values of f are evaluated at the left endpoint x0 and the right endpoint xn. And so that's a total of n plus 1 points. So that's a odd number of points. So for that reason, this pattern of coefficients will always look like this. So it will start with 1, 4, then there will be a sequence of alternating 4s and 2s. Then at the very end, we have 4 followed by a 1. So the total number of coefficients is odd, and so for that reason, we'll have always the one but last term always being 4. So it is interesting to check that actually, if you add up, if you take the Simpson's sum for n equals 2k and look at it closer, you can represent it as t of k plus 2m of k. So we're not going to verify it, but that's basically the situation. So when you look at the midpoint sums for k, you get to evaluate f at the midpoints of these k intervals, and the midpoints of k subintervals end up being precisely the endpoints of the 2k subintervals, because what happens when you go from k subintervals to 2k is just you're subdividing every subinterval into 2. So this is the relation between the Simpson sum and trapezoidal and midpoint sum. Now, as I explained earlier, what it implies already is that Simpson's rule, approximating integral with the nth Simpson sum, is going to be much more precise than were the two previous integration rules. And so that is indeed the case, as can be seen from this error bound for the Simpson's rule. So what it says is you have some control on the fourth derivative of f. So this superscript 4 in parentheses denotes fourth derivative. So if you know that the fourth derivative of f of x is not larger than some constant k on the interval of integration, then you can control the error of the Simpson's rule. So again, by error we mean the difference between the true value of the integral and the nth Simpson's sum. And so this error is at most k times b minus a to the fifth divided by 180 n to the fourth. So the key term here is n to the fourth. If you recall the error bounds for trapezoidal and midpoint rule, you will see that there n appeared with the second power in the denominator. Here it appears with the fourth. So this means that Simpson's rule is indeed much more precise than the two other rules, than the trapezoidal and midpoint rule. So specifically, this is due to the fact that you're dealing with functions that have more derivatives. So somehow the assumptions of Simpson's rule is that you can look at the fourth derivative, so that means your function is much nicer, much smoother than it was assumed in the other two rules. So that means that it's much more amenable to being approximated with little pieces of parabolas. So this rule is actually quite practical, and it's often used for numerical computations. And we will look at some examples of how the Simpson's rule, trapezoidal rule, and midpoint rule are used for computing actual practical integrals in some common computer algebra systems. So that comes in the next video.